And we've derived the compressibility corrections. And now we are using the derived compressibility correction methods and then implement it into the graphical method to calculate the critical Mach number. Okay, so this is from the previous slide. And what we did is um, to do multiple high-speed measurements and then find the CP minimum and then get such a connections of the measurement points and then find the cross-section between the two curves, and the cross-sectional point Mach number is a critical Mach number. And then we asked one question: is there a way to do fewer number of measurements to get the critical Mach number? The answer was yes, and the answer was to do a single measurement in a low speed flow, as highlighted through the star. And since we already have the correction, pressure coefficient correction using the compressibility correction method, there are three we introduced. So we can apply those three methods into here and then get these similar points as the red ones in here. Okay, so now the updated graphical method. Step 1 is measure the airfoil at low speed and find the CP0 minimum. So we can do such a measurement and then get the minimum pressure coefficient. And step 2 is carry out compressibility corrections and generate a MACP curve. So we can apply the common chain rule or Planck-Galois rule or the Layton's rule. So whatever method we use, and we just implement the corrections and get such dots at different Mach numbers. So in here we did the correction at 5 Mach numbers, and then we can do such correction. Okay, so again, the cross-sectional points, the Mach number at the cross-sectional points is the critical Mach number. So this is updated graphical method. And I think it's more convenient than the original one. Instead of doing a couple measurements, we are just doing one measurement. It's more convenient. But apparently there's a bit uncertainties because of the uncertainty in the pressure correction, right? So we need to accept that fact. And now I don't know whether you realize the problem. We do the correction, and the correction is always based one point. Is there chance if the minimum pressure point moves when you increase the Mach number? So this is a very important point. Are the locations of minimum pressure or CP minimum at different Mach numbers the same? Okay, so now let's demonstrate through an example of a NACA 12 airfoil. The angle of attack is 0. And we know for NACA 12 airfoil, the maximum thickness is at 30% of the chord. And so let me ask, where do you expect the minimum pressure appears? It's upstream, downstream, or exactly at the maximum thickness? And the answer is it doesn't overlap with the maximum thickness point, but slightly upstream. Okay, so let's see the three measurements. It's this airfoil at 0 angle of attack and measure at 3 Mach numbers, actually 3 speeds. So one is low speed, we can treat it as incompressible flow. The Reynolds number is 3 million something, and then the Mach number increased to 0.575. The Reynolds number also increased, and the Mach number eventually become 0.725, and we have Reynolds number 5 million something. Okay, and you can see for all the three cases, the minimum pressure always happens at 11% of the chord. So this demonstrates the minimum pressure location doesn't vary much with the Mach number. Okay, so now we get two conclusions. One is that the minimum pressure location does not necessarily overlap with the maximum thickness. Second is the minimum pressure location does not vary much with increasing Mach number. So these two conclusions can allow us to apply the graphical method using the compressibility corrections confidently. And the final thing we need to address is the aerofoil thickness effect to the critical Mach number. So this is a kind of two curves in a graphical method. One is for the thick airfoil, the other is for the thin airfoil. And if again we start doing the measurement in the low speed, apparently thick airfoil has larger curvature on the surface. Then the minimum pressure is actually smaller than the thin airfoil, so it stays higher. Remember, the y-axis is inversed. Okay. Then we just continue applying the correction method, and we will notice the critical Mach number for the thin airfoil is larger than a thick airfoil, and this is beneficial. And so that a larger critical number delays the appearance of the shockwave. So that also explains why for high-speed or transonic aircrafts, thinner airfoil is preferred, because we can have larger critical Mach number. So the reason the thin airfoil has less disturbance, and it confirms with small disturbance assumption more. Therefore, the maximum pressure drop is smaller. So using the graphical method, we can explain why the thin airfoil has larger critical Mach number than the thicker airfoil. So now we can close the graphical method, and hopefully you can have a good understanding about the graphical method. And we started with the original method, and then we did some preparations such as pressure coefficient and the small disturbance assumption, and also the derivation of the plant gauge assumption correction. And then we introduce the updated graphical method. Eventually, we use a graphical method to explain the difference of the thin airfoil and the thick airfoil for critical Mach number. So this is a story of the graphical method to estimate the critical Mach number. Hope you enjoy it.